Hello, welcome to the first episode of this operating system development lecture series. Today I'll be talking about some basic prerequisites, about the goals of the series, and I'll try to answer this question of, well, we're going to make an operating system, but what even is an operating system? What are we going to create? So I'm going to start by talking about the prerequisites for watching this lecture series. I will assume that the viewer knows basic computer science. What I mean by that is this series will not answer questions such as what is a CPU architecture, or what is a bitwise shift, what is a logic gate, what is an positional system of writing numbers in a given base. What are opcodes, what are operands? Questions like these will not be answered throughout this series. So I hope that you have studied computer science, hopefully even in a formal setting. Although that is not, it is not required that you studied it in a formal setting, obviously. And I will assume that the viewer is a competent programmer. And again, what do I mean by that? This series will have a lot of practical information on how to actually develop an operating system. This is why I have chosen to call it an operating system development lecture series, and not just an operating system lecture series. I will assume that the viewer can code in assembly, and even in a higher level language like C, C++, Rust, whatever. So this will be assumed. So those are actually all the prerequisites. Usually you'll encounter the fact that you should know more before making an OS, but I'm talking about the bare minimum. Obviously, any extra knowledge, such as about executable file formats, bonus knowledge about x86, stuff like that, it's obviously going to be helpful, but it's not necessarily necessary. It's not necessary for comprehending most of the content of these lectures. Now, so what are the goals of this? What am I trying to achieve with this? Well, I want to show some practical information regarding how to make an OS, whilst also giving this theoretical info on it. Well, pretty much only giving theoretical info, but enough that you could make an OS with probably some amount of research, but probably not as big of an amount of research. And I might even make a separate series. I'm actually considering that after this one, a series where I'll actually program example implementations of what I will talk about in this series. But what I'm trying to do is give this theoretical and practical info on how to make an OS, and because of the fact that I will try to give practical information, this will get specific at times. And this is why I want to state up front that I'm going to be focusing on an x86 legacy BIOS operating system. So a lot of the content of what I'm going to record is definitely not going to just be accessible on x86. Most of it does not require a legacy BIOS. That's only going to be necessary on the beginning. And maybe later I will talk about adding some stuff to the bootloader, but that's not that important. Point is, I will be focusing on some specific technologies and not just talking about OSDev in general. That's necessary to provide a practical perspective. So before anyone critiques it for being narrow-minded for only explaining x86 or for not using UEFI, well, I will explain UEFI, but most of it will not be based on UEFI, most of the other boot stuff. Before anyone critiques it like that, I just want to point out I'm mainly trying to use those technologies, and that's what I'll be basing on. If somebody wants to use something else, if somebody wants to use UEFI, they have to do a slightly larger amount of research. Okay, so those are the prerequisites. And I explained a bit about the goals. So I said I want to make this x86 legacy BIOS OS, but the thing is, what is an OS, right? And I'm going to provide a certain definition, and I'd just like to say that I recommend taking notes during all of this, so that no rewatching of entire videos is required. So I'm going to provide this definition, and I'm going to format it in a specific way, which I'm going to elaborate on. So, an OS is software that allows the user to run programs while managing, and I could write the following resources. Those are all going to be some sort of resources, but I'm just going to say while managing. I/O devices, memory, CPU time, and data, which is intentionally vague, and I'm going to come back to it. So the reason I formatted it like that is you could actually place 6 places for check marks. And the sentence, well, over here, it actually cuts it off because there's no more space on the board, but that wasn't necessarily my idea. I was going to split this sentence in half anyway. The reason for that is making an OS which runs programs and making then the user actually be able to execute the programs by themselves are 2 completely separate things. So I just wanted to point that out. And you will, far before implementing something like a shell, or just any user interface, run some programs on your OS. Okay, so the resources that the OS has to manage, right? I/O devices, memory, CPU time, and data. If it comes to I/O devices, I think that's pretty clear, because, well, you can have an OS and it can, perform logical operations, and you can have this entire logic of an OS, all the algorithms, everything. But it would be pretty lame if it could not interact with a user in some sort of sense. In fact, according to this definition, pretty arbitrary definition that I gave, we need some kind of user to actually interact with our operating system. So how can the user interact? Well, it needs to give some input so that the OS, isn't just a pre-programmed thing that does the same thing every time, and the user can actually influence it. It needs some input device, and then so that the user can get any feedback that is actually valuable, and not just the computer doing something, and the user doesn't have to take an actual voltmeter and stick it and measure the voltage. You need some output device, So we all have to manage I/O devices. So, for example, write a keyboard driver, a mouse driver. Have a user press a button on the keyboard, move with the mouse, and then give a corresponding feedback. For example, for the monitor, or it could be sound, so it could be some speaker system. Right. Memory. By memory, I really mean the random access memory. How we should interpret this is it is really just a workplace for the programs, for the processes. So you have an OS, and it's running some programs, and each process, which is basically just a program running, right, has some allocated amount of RAM. And it is supposed to use it as this resource, which is just its workplace, really. So this amount of RAM, it can place some results of computations, it can store some variables, stuff like that. So really just this workplace or workstation of every process is going to be the memory. And it's important to state it like that so that I can later talk about the difference between memory and data. But first let's talk about CPU time. Okay, so what the CPU does, right? This should be clear. Is it has some sequence of instructions, and the CPU just execute. You have some sequence of instructions, and the CPU just does this sequence of instructions. The thing is, in a modern operating system, you obviously have some sort of multitasking. And well, how do you do it, right? You have multiple sequences of instructions, and all of them want, quote unquote, to be executed by the CPU. So you treat CPU time as a resource to also be managed by the operating system. So each process, each set of instructions to be done is allocated CPU time. And there are different algorithms for that, which I'm going to cover. It gets even more complicated when you have multiple CPUs or multiple cores, right? Because then you have multiple CPUs, and you have to give out CPU time from over the core software-wise to those processes, right? And then there's data, which is pretty vague. I mean, what is data? It could as well just be the variables in the random access memory, right? So what do I actually mean by data? Well, by data, I mean just large chunks which are supposed to be processed by the OS and usually in some way interpreted by the user. What I mean by that is stuff like text or images, executables, audio, things like that, right? Those are all things by which I mean data. And you might think to yourself, if you think about your daily computer usage and you hear stuff we have text, audio, stuff like that, the first thing that probably comes to mind is those are all files. And unless it's vague, but I could have just written while managing the file system. That would have been correct, because that's basically what I mean by data. By data, I mean you have a file which stores some audio data. You have like a video file, something like an MP4 or MKV. You would have an executable file like .elf. So you could really say, while managing the file system, so the reason I left it as data is because I wanted to be more general, because there are, in every practical context, yes, you're going to implement a file system, but I kind of want to point out that a file system, and the idea of a file, is a sort of abstraction on top of the ones and zeros. What I want to say is, in theory, yes, you could organize the data in some other way, and the OS still is going to manage that as a resource. So for all intents and purposes, you could replace this data with just text that says the file system in this definition. Yeah. So I'm going to try to, what I mean by I'm going to show you how to make an OS, I mean I will try to show you how to make a bare metal software for x86 and the legacy BIOS that is going to end up ticking these 6 check marks. So this is what I mean, right? Yeah. Okay. So I kind of talked about the goal and what I mean by an OS. What I mean by we will try to create an OS. But also, you might realize that an OS is pretty big, right? It usually has thousands, tens of thousands, hundreds of thousands lines of code, right? And well, treating an OS as just a standard, like, procedural sort of set of instructions, this very pure interpretation sort of change on the larger scale. So it's good to have your project organized in some way. And I'm going to present how, like, pretty much 99% of OSs are structured. It's an arbitrary number. But I'm going to show a pretty general structure and then go into some other variants which you can choose. Obviously, you don't have to be limited to the variants I provide. So I'm actually not going to start where a lot of literature starts. I'm actually going to start in the user space, alternatively called the userland. So the user space is basically what you get to interact with. So right now, the moment you're watching this video, you're in the user space of your operating system. It's the space dedicated for the user. So it's good to start with this because this is something you already understand, and in fact this is something you have a very good intuition on, because you most likely use this very, very often, assuming you use operating systems often, which, I mean, it's not an exaggeration to say that most people in advanced countries might as well even use it every single day. So we have this user space, and how do we get from a process running in the user space to actually doing anything hardware-wise? Well, the idea is to have this core part of your operating system, which is going to manage your resources, which is going to interpret the different things coming from programs. The sort of core, this something that even could be considered your OS in some vague sort of sense. this core fundamental part of an OS is called the kernel. So this is a kernel. And well, I'm going to connect the user space directly to the kernel, but this is an oversimplification, and I'm going to explain later in this video why it is, but I'm just going to go with it for now. So, okay, so we have this kernel, which can manage those things for us, but how does a user space actually communicate with a kernel? How does it work? Well, a user space simply sends a signal. The signal, to be exact, is usually an interrupt, but we're going to talk about that later. It sends something called a system call, also called syscall for short. And this is basically a request to the kernel. It requests for something to be done. And one other motivation for this to even be done, right, and the reason why you couldn't just do everything in the user space is because, well, the user is supposed to have minimal permissions. Well, not just because, you know, it's not just because many OSs assume that their user is an idiot. I'm not going to list out any names here. But it's not even because of that. It's because a user could simply open a file, a malicious file, something we know colloquially as a virus, and that virus could, for example, well, if it had full access in the user space, just very easily wipe out your entire hard drive. Because, well, if it had all the access to your hardware, it could just send some requests through interfaces like IDE or HCI. It would just send them. It would just tell the hard drive to override everything with zeros, and your data is gone. So yeah, that's a bit problematic, and we don't really want that. So we want to give the user space minimal permissions. And the idea is that the kernel itself has the highest permissions possible. And the user space, when it wants to do something, it can communicate with the kernel and can say, hey, I want to do this high privilege thing. And the kernel can check, depending on the security system of the OS, okay, I'm going to check if you can actually do that thing, depending on, for example, the user permissions, what program it is, etc., etc. And if it passes the test, quote unquote, then the kernel actually does that. And that's basically the mechanism. So you have the user space, it wants to do some user space instruction, but it has to call the kernel verifies that that can even be done, does that, and then it goes to the next instruction in the user space. So that's the general idea of it, except there's actually an extra element of abstraction, usually, something called a driver. So I'm just going to draw a connection between the kernel and drivers. So I like to make this comparison, right? Think about a car, right? When you have a car, it can do cool stuff. It can go at high speeds. It can transport you to different places. But if it's just there, then it's just there. It doesn't do anything by default. It's just a bunch of metal, right? It doesn't really do anything. And those are all of your electronic devices. That's the comparison I like to make. So when you have your mouse, by default, it doesn't actually do anything. It's just a bunch of plastic with some electronic circuitry. And the thing is, you need something to take advantage of all that circuitry. So in a car, that would be done by a driver. A driver would, launch the car and be able to actually drive it, right? Use it. And that's the idea of a driver if it comes to electronic devices, peripheral devices, right? So we have a mouse, and it needs some driver, so it could, for example, initialize the mouse, then actually interface with the mouse. Cool, we can actually use the mouse, it's not just a bunch of plastic. So usually this abstraction is added in some, as I'm going to talking about in a second. You could consider the drivers a part of a kernel, or you could not. I'm going to talk about that in a second, but so just to update our idea of how an OS operates generally. Right, so we have some user space program, it has some instruction to do, it does a system call to the kernel checks if that given thing requested by the user program can even be done. If yes, it does it. Well, let's say the requested thing is closing a window, right? So it checks, can the user close the window? Well, sure, yeah, it can close the window. That's a pretty basic thing, right? So, okay, it can close the window, and for example, it can't display the window anymore, right? Because it's closed. So it contacts the graphics driver and just says, hey, just don't display that window anymore. And this is done. And then next instruction, and the same mechanism. Cool. So that's how an OS operates. One tiny problem. Okay, so we have this cool abstraction, but we have to remember our OS is still fundamentally a series of instructions. It has to start somewhere, right? The code has to end somewhere. It's still a series of instructions in a sense. So it has to begin somewhere, right? You're not going to have this entire system by default. You need something to initialize it. You need something to load the kernel. So this initial program that is responsible for initializing this right after boot is something called a bootstrap loader. Well, that's a name you'll encounter in literature, but it's not that common anymore. Most people in the OSDev community nowadays call it just a bootloader for short. So you have a bootloader. You have a bootloader, and it simply loads your kernel. Yeah, so that's a pretty general structure. You have a bootloader, it loads your kernel, but we have this entire mechanism where programs from the user space will contact the kernel for system calls, and the kernel will do everything that the program asks for, if it is permitted to do so, right? Yeah, so I think that's everything I had to say about this general structure, but as I said, it's pretty general. So it highly depends on how you will actually want to design your kernel, right? Because since your kernel is the core part of your OS, then how you design your kernel and what it actually contains is going to be a huge dependency for what other components is your OS going to have. So I'm just going to be talking about what I think are the three most common kernel designs. There are other like kernel designs that you can research, such as exo kernels, which I'll not cover here. But these three are the ones that are the most common, really. Most OSs you'll see will have one of those three structures. So one very common structure that you have is a monolithic kernel. A bit of etymology, right? Mono meaning only or one in Greek, and then lithic coming from the Greek lithos, or rock, stone. So you can kind of get the idea that in a monolithic kernel, the kernel is this one big stone or rock. You have one big kernel. and it has pretty much all the functionality. And you just have a user space. And the user space communicates with the kernel. And that's it. That's the whole structure of a monolithic kernel. It literally has everything. It even has drivers. They could be separated, but they're still often interpreted as a part of the kernel, in a sense. So it's very general architecture still. Well, not architecture, the design or design philosophy. But most of like the common drivers at least are considered part of the kernel. The user space communicates with the kernel. The kernel does everything. Next instruction for user space. Simple. Then you have something called a microkernel. So it has a sort of different idea. You have the user space, which is the least privileged. And you do not communicate directly with the kernel because the kernel, as the name suggests, micro, is very small. So you have a very small kernel. Instead, you communicate, yeah, conjugation, cool. Instead of communicating with a kernel, you communicate with a driver if you want to contact the device, and a server if you want to contact some other kernel service or like OS service, right? So the idea is that the kernel doesn't contain, for example, all the logic for all the drivers and OS services. Only contains the bare minimum of the fundamental functions. That's all that the kernel contains. Then all the logic of like drivers and services, it's contained in the drivers and servers, which are just programs. So you just have programs. You have servers. I'm just going to write serve for short. And drivers, we're just going to write DRV for short because of the lack of space. That looks like a P or something. That's strange. I'm going to erase that. You have a driver. And the idea is the user space first communicates with the servers and drivers, and they communicate with the kernel. So that's the idea. So it doesn't directly communicate with the kernel, right? All the logic and stuff is handled by these two. Yeah, and if it comes to privileges, the kernel still has the same privilege as a kernel in a monolithic design. The user space has the same privilege. If it comes to servers and drivers, they're not programs with the same permissions as a classical program in the user space. In the sense that they have a privilege between user space programs and the kernel. But they're still just programs which have to communicate through syscalls with the kernel. So they just have a bit more permissions, but just the stuff they need, right? Okay, so that's a monolithic and microkernel. One other design is a hybrid kernel. So this is a pretty interesting design. You still have a user space, obviously, and you still have a slightly bigger but relatively small kernel. And the idea is you still have some servers and drivers. So serve and driver. And they do communicate with the user space, and then the servers and drivers communicate with the kernel. However, some of the services offered by the OS don't have to be actually accessed for servers. Some of the servers, which were in a microkernel design, just programs running with this, in between quote unquote privilege, are in the kernel. So for some of the functionality, you are going to interface with the kernel directly, and for some functionality you are going to use servers and drivers. So it's this hybrid, as the name suggests, of this monolithic design and this microkernel design. Yeah, so I hope I have shed some light on those kernel design philosophies. And, well, you have to pick one. It's good to pick a kernel design philosophy early on. I would just like to state that most of the ideas I'm going to be portraying in this series are going to be somewhat based on a monolithic system. I didn't mention that previously when I talked about the goal of the series, because I don't think it's that important. As in, just by knowing this structure of a microkernel or a hybrid kernel, just knowing this idea, you can easily convert things I'm going to say about monolithic systems to micro and hybrid kernels. So I just wanted to point that out. Yeah, but conversion would be really easy, and if you still have trouble, just use some well-known microkernel or hybrid kernel as a reference. Just take a look at the code. Yeah. So choose your fighter, I guess. Obviously, you don't have to pick any of those. You theoretically don't even have to follow the structure on. Well, not the previous slide, but the previous diagram that I presented. But it is very common, and most likely, no matter what you're going to make, you are going to resemble that previous structure in some way. Yeah. So I talked about this kernel design. We answered the question, what is an OS? I think this is a pretty satisfactory introductory video to this lecture series. And next time I'm going to actually be talking about how to make something that boots on the legacy BIOS and the UEFI BIOS. Well, a bit less about the UEFI BIOS, but I will talk about the general idea and then give more specific information about the legacy BIOS. So, booting might not sound like much, but I know people who say that some of their simplest OSs that barely booted, well, they weren't even OSs, it was pretty much just like x86 bare metal code. That booting, like a very simple, something that even might just be a hello world or their name in a VGA text mode, right? That were some of, till this day, some of their happiest OS of moments. So getting an OS to even boot is pretty cool. Well, I'm not going to be talking about how to display Hello World yet. That's probably going to be in the third lecture. But yeah. And just to finish us off, I wanted to talk about maybe even this philosophical, in a sense, dilemma about bootloaders. Okay, should I use some bootloader? If yes, what bootloader? I would say this is a difficult question. But the general consensus is that you should use a bootloader made for you. Because, well, you're obviously not going to make a great bootloader as a beginner. But the thing is, it really highly depends on your goal. I mean, you're not going to learn much by making a bootloader because the stuff you do when making a bootloader is not actually useful later in OSDev. And you will have to struggle with quote-unquote hazardous environments. So you might want to use a bootloader, and one that I recommend is Lemonade. I mean, everyone uses it. It's a great bootloader, really. So use Lemonade, but if you're just trying to make it for fun, and you want to test yourself, oh, can I make a bootloader? Or wow, I just want an OS with a bootloader. Really much, I think it would be like extremely fun. Then don't let any opinions stop you. This is really more of like a philosophical thing rather than anything technical. But I would still like to point that out. I mean, if you just think you're going to have some fun with a project, and some people say, no, this isn't necessarily the best solution, but still really want to do it, and it's something not that serious, and you know that this is not the best solution, do it. I mean, you might develop some bad habits, but I mean, writing your own bootloader is not really a habit. I mean, it's a one-time task. You think to yourself, wow, I've made this. I can't really use it later on because it's not that advanced. I think I'm going to use something else. Or you go really, really deep into bootloader development. Just do what you want, really. I'm going to provide primarily just technical information, and I will talk about how to make a bootloader. And that's because I think it's a vital part of understanding how a whole, well, perhaps not how a whole OS functions, but I really want to talk, how can you just make pure x86 bare metal code that is going to do all these functions? And if I want to show you how to make this x86 bare metal code that would do that, I can't just say, okay, we're going to skip all this important stuff that goes into booting and just start making a kernel. That will go against the idea that I have for this. So I will give info on how to make a very basic bootloader. How you use that knowledge is up to you. You could make your own bootloader, you could test yourself, you could see it, you could do it as a fun project. You could not do that. You could stick to your bootloader. I'm not you. You go ahead, you do what you want to do. I am going to provide the technical information. Yeah, so I think that's everything I really wanted to say in this lecture. And I hope that you watch the next one about the booting process, where you'll find out what happens when you press the power button on your computer. Yeah.